Thank you. Good afternoon to all. Thanks for coming. As she said, my name is Hugo, and for the last 3 years and a half, more or less, I've been working on a personal research involving aviation security. Today, I would like to share with you some of the results of this research. So, let's go. This is not the typical slide where I explain who am I, but the idea is to explain what am I. I think that's important for what I'm going to talk about, because on one hand, I'm IT security researcher, as most of the people sitting there. But on the other hand, I'm also commercial pilot for the last 12 years, and I needed both of these knowledge in order to face this research. Even being commercial pilot, I had to study a lot for many time in order to deeply understand aircraft systems and the inner workings. So take into account that for the rest of the talk, as most of the concepts will be new, and I won't be able to explain everything. Okay, the agenda for today, I've divided the talk in two different parts. The first one, we will see how to get vulnerabilities on systems on board the airplane, and after that we will see how to use those vulnerabilities in order to exploit those systems on board the airplane. Just before beginning, I know by the end of this talk most of the subjects will be not properly explained, but I have time constraints. Aircrafts are quite different from computers, and I'm sure that not everybody here has all the background, all the knowledge necessary in order to understand everything. And also because, due to safety reasons, I cannot get into the details on, for example, the vulnerabilities or the exploits, because most of them, not to say all of them, are still pending to be patched or solved. Okay? So let's get into part one, where we will see how to get those vulnerabilities and how everything started. Everything started, as I said, many years ago with one question. The question was if I would be able to convert for security, from the security perspective, an airplane into a computer. So get some of the onboard systems, try to find vulnerabilities, develop the exploits, and see what may I be able to do once exploited the onboard systems. The question to this answer was yes. And many years later, this is a brief map of the main topics I have been covering, or I'm covering right now, or I plan to keep doing research on this time. As you can see, I have divided that on vector, attack vectors, targets, all the common phases of an attack. From all this, today we just can talk about a few points, a few systems, a few targets, and a few protocols. Not everything can be covered, okay? Take into account. This is what we are going to see today. The attack overview for today is, I have organized that into the common phases of an attack, which are discovery, information gathering, exploitation, and post-exploitation. For discovery, we will use a well-known protocol called ADSB. For information gathering on the targets, we will use ACARS. And for exploitation, we will use ACARS to reach the airplane and exploit onboard system vulnerabilities. After that, we'll see the post-exploitation options we can have. So let's start with a brief introduction on ADSB, though I published recently a paper on that, a small post on that. ADSB stands for that Automatic Dependent Surveillance Broadcast. It's kind of a radar substitute that is being deployed right now all around the world, and gives information as position, velocity, speed, identification, and information to air traffic control and management back on ground. ADSB has a data rate, more or less, approx of 1 megabit per second, and we will be using that in order to locate and plot targets on a map. Let's say it's like an ARP ping or a discovery scan that you can do with Nmap, just to know which targets are out there. Okay, talking about the DSB security, that's easy, there is not at all. So you can find almost every kind of attack you can find on other common protocols. by the end, on the reference slide, you can see links to other documents that explain all those attacks. Okay. As I said, we will use that in order to get target selection, and we will use 3 different sources for this data. First, we will use public databases, a lot of people gathering ADSB data and sharing with us, local data using software-defined radio, and we will be working all the time on this research with virtual aircrafts. We'll see later. So we'll also take the ADSB input and output of these airplanes. That's all about ADSB security and how to get the targets on a map. Okay. After that, we will use ACARS. ACARS it stands for Aircraft Communications Addressing and Reporting System. It's kind of, it's been described like an email system between ground and airplanes, and also between airlines, ATC. Almost everybody involved in aviation can use ACARS to communicate between them. Okay, and we will use that in order to give kind of operative system fingerprinting of the selected targets by just gathering as much information as possible. By getting ACARS data, we will try to get detailed information on the available targets. Relating ACARS security, we have exactly the same one as on ADSB. People, mainly military, are working on some secure implementations on ACARS, nothing deployed. As far as I know, some airlines have tried to develop or implement their own kind of security, like the one I said here. To be honest, I think that cannot be considered secure anymore, but you can find it if you just gather information from public databases. As happens with ADSB, there is a lot of people just gathering ACARS communications and sharing them. Local data by using software-defined radio again, and of course virtual airplanes. That's what we are going to be using. Okay. Finally, regarding ACARS, I have to mention the ground service providers, which are 2 big companies that offer worldwide coverage of ACARS related services. We'll see later on part 2 a little bit more about that. Okay, that's a brief introduction on those 2 protocols that are not the target of this talk, just some resources we will use in order to get into the airplane. By the end of these 2 phases, we will have a map of available targets. We will have detailed information on most of them, so we can try to guess which one are feasible for our purposes. Now, the FMS, the Flight Management System, is the onboard system we are going to target today. There are many of them, but today we are going to focus on that one. Usually it's consisting on 2 units, components, a computer unit, that's the one you saw below on the left, which is just inside the flight deck and you don't see it. And on the other hand, you have the control display unit, which is this one with the keyboard and the old screen in green and black. It's used by the pilots in order to enter data and get some feedback on the flight management system operations. Okay. I also added another image of the electronic, one of the primary flight displays of the airplane. You know, all these screens that you can see on common cockpits on airplanes. This is one of them, and some of the data output by the flight management system can also be shown there to the pilots. Okay. The FMS, brief introduction. Our goal is to exploit the FMS, one onboard system. The idea is to use ACARS communications to upload data into the FMS. And there are, as we'll see later, many different data types that we can try to send into the FMS to try to find vulnerabilities. The different upload options we have are software-defined radio for local area targeting, or ground service providers to try to cover worldwide targets. Okay, the path to exploit, as always, is get the aircraft code, search for vulnerabilities, code the exploits, and then try to deliver them. For that, and for safety, security, and obvious reasons, I don't have an airplane at my apartment. We will use a virtual environment to set up virtual airplanes that will use actual real code, software, and hardware from different airplanes. So, how to get this hardware and software may look difficult and expensive at the beginning, but it's not that much. There are different resources we can try to use in order to get this hardware and software. For example, the always helpful eBay. If you go to eBay and search for airplane systems, onboard systems, aircraft systems, you will see hundreds of them. You can always go to some scrappings, like the Russian ones, where you can just point to an airplane and point to the systems you want, and you can just even ask for 100 kilos of airplane, and you can have almost everything inside. I also learned to love Salesman because of these products that are not the airplane systems by themselves, but they interact with those systems. We will see later that they also can help us in order to get detailed information, if not the product itself. And also, if the manufacturers are secure, so you cannot get the hardware directly from them, the software directly from them, you can always face the third-party vendors, which usually have less security and they're eager to sell as much as possible, so maybe also useful. Finally, as always, the resourceful users or former employees are a good source of information to try to get, if not the hardware itself, maybe a firmware update. You can always get into a specialized forum of the product you are looking for and say, as happened to me once, yeah, I got this product, but they got a new version, so they don't give me the update of the previous one, so I'm completely fucked up. Suddenly another person says, yeah, that exactly the same happened to me, I'm completely pissed off, but don't worry, I will help you. I have the firmware update you are looking for, and you can have the firmware update of an aircraft system, which is always a good vector. Okay, some examples. For example, you can find on eBay a Honeywell flight management computer for $400. May seem quite expensive. We'll see later other examples. Cheaper, like this airline system for just $15. $85. It will get cheaper. For example, you can always face another approach, which is the training software. That's where I learned to love the Salesman, because on the specification of the product, they always try to give you as much information as possible in order for you to buy this software. So you can see things like our solution uses the same software that is used by the aircraft, by the actual Rockwell Collins FMS. Usually these training solutions are cheaper also. The same happens, for example, to Honeywell. High-resolution graphics are combined with actual aircraft code to create the training environment of your dreams. Fine. Teso Aviation also. You can see here an ACARS aircraft management unit for just $10 on eBay. I got that one, by the way. The only problem is that it's heavy and it's hard to get it sent back to Europe, but you can for sure find some way to get that delivered to you back in Europe or wherever you live. Another example of another software, in this case for data link simulation, Honeywell also says below the AirSim incorporates over 95% of the actual CMU and HCU software. So another product, training product with real airplane systems code. Okay, and another one. For example, the first software I got for the flight management system was this one that can you see on the top. I got it from a game shop in Ohio for $10 because they thought it was kind of a plugin for the Microsoft Flight Simulator that was not anymore on sale, so they just sent it to me for $10. That's how I get the first flight management system code. Okay, fine. Now we have the software, we have the hardware for ACARS management computer units, for flight management computers and other systems that we can decide that we need in order to replicate that. So yeah, it's properly seen more or less. We can set up our lab. For example, in my case, I use a laptop with Inguma, a security research framework I developed that using Python C types talks with this software. Also, each virtual airplane aircraft I set up has its own software-defined radio communication to simulate the ADS-B and ACARS communications, both ingoing and outgoing. And in order to make more realistic the environment, all the virtual airplanes are gathering actual real flight data from another computer running the X-Plane flight simulator, which is a really good flight simulator, and with a plugin you can get and connect those virtual airplanes with it. So you can really make them fly to see how they behave, not just in ground. That's useful for example, the exploitation and post-exploitation. We'll see later. This is a picture. Usually my lab is not that well organized, but for the picture I improve a little bit. You see this laptop with a X-Plane. This huge laptop is the one running X-Plane. The middle laptop is the one that usually takes care of all the software-defined radio stuff. And the small one usually has the research environment, some virtual airplanes, and it's connected to the other two. Also, you can see some autopilots and other hardware, like a Raspberry Pi, I used to run separately other systems and components where I need that. On the top of that, you can see a small ADSB receiver and the USRP software-defined radio peripheral and the antenna. Okay, so we have our lab setup. We can set up virtual airplanes using real code, real aircraft. We have real communications using software-defined radio, and we have our environment to try to find vulnerabilities to the airplanes. Everything ready. Let's try to find the vulnerabilities, okay? So what we have to face in order to find vulnerabilities on the flight management system, computer mainly, is that we have many different vectors, approaches, which are the different data types that can be uploaded into the FMS via ACARS. There are many flight management system manufacturers. Each of them has models and different versions. So we have to try to cover as much as possible of them, the architectures. Usually real hardware uses kind of PowerPC or other systems. Our lab is using different code, but also depending on the system, if we are targeting the FMS of real hardware, real code, but compiled for the x86 platform. The language, that's funny. I don't know if you ever tried to do reverse engineering on an ADA binary. I did, and I got a manual for that because I had no idea how that language was. Another problem we have is the operative system. This is real-time operating system realm. It's mainly for the older devices. They use the so-called digital engine operating system, which is an older real-time operating system developed together by, if I'm not wrong, NASA and Honeywell back on the 70s. And on the most modern devices, they are moving to other real-time operating systems like VxWorks. Okay? Also, as our vulnerability and exploits are going to be delivered via ACARS, we have to take into account that ACARS has a delay, an average delay of 11 seconds, more or less, approximately. The size of the maximum size of an ACARS message should be around 220 characters, and you can use up to 16 of them that will be merged together up in the flight management, in the ACARS management unit on the airplane. At least in order to deliver the exploit, you have to take that into account. After that, if you take control of the ACARS incoming messages, you can just forget about this. But at least for the exploit delivery and the first stage of the payload, you have to take that into account. Also, looking at the images, you see that the ACARS messages are usually encoded. So even if you prepare your ACARS message, malicious ACARS message, you have to take into account that you have to encode that in order to upload that into the airplane. And after that, it will be decoded and it will be transformed somehow until it reaches our final system, in this case, the flight management system. Okay. So which kind of data can we send? This graphic here, offered to us by CETA, we'll see later who is CETA, shows up some of the standard information sent and received by an airplane during a normal flight, all of the phases of the flight, from taxi to landing and again taxi, okay? You can see two aircraft. That's what we are interested in because that means the information is being sent to the airplane. Okay, you can see that a lot of information is being sent and exchanged between airplanes and ATC, traffic control, during a normal flight, but during takeoff and landing, which are the most critical phases of the flight. Also, even if you see a lot of information being sent here, take into account that this is just the normal operations and the normal communications. Also, during exceptional conditions, additional information is being sent. Airlines also send and receive information using ACARS also can be used. Maintenance equipment also use ACARS, all other information that can be used. A lot of information can be used. I mean, the surface is quite big. Just get one of those and start fuzzing or whatever, your favorite procedure. Okay, now it's time for a demo of this virtual environment I have set up. I will show you the Inguma framework I have, the specific version for this development research, okay? Here, okay. This is the Inguma framework. This is the first tab you can see on the left. That there are many tabs: networking, terminals, reversing, exploiting, and planes. Planes is the important one, the one that you won't find on the public available version of Inguma. Here you can see the IP addresses of all the computers that set up my laptop, okay, the ones I showed before. Here we have many terminals. This one actually is showing all the data being received by X-plane simulator and being sent to the virtual airplanes to make them fly. Okay, we have another terminal with Radare tool, reverse engineering tool that I use in order to reverse engineering, mainly debug the software, the code while sending the malicious crafted messages. And on the last one, I don't know if we be able to read that. Let's wait until I highlight that. Yeah. This is just the command prompt of the post-exploitation agent that we will see later. And I just have always a terminal to try to manage the airplanes once exploited. On the reversing tab, we have some code open for static analysis to try to follow what's going on. You can see the functions, the imports, the exports, the sections, the normal stuff, okay, of this binary. As you can see here, this is a normal Windows binary because this is one of those codes that use real aircraft code but have been ported into the x86 platform. Okay, the exploiting tab I use mainly for the fuzzing stuff. You can see that I have ACARS and ADSB different probes. I have here selected the ACARS, and each of these fields will be modified and sent into the virtual airplane to see. Okay. Now, back on the important one, the planes one, on the right, you will see that we have three tabs: ADSB, ACARS, and exploitation. On this ADSB, actually, right now we are seeing some airplanes being gathered by software-defined radio on the Berlin area, and detailed information we can gather by just sniffing a little bit of ADSB. We can also face this other application that you can find on internet that allows you to have a broader coverage, in this case worldwide, more approximately. So we can also face additional targets. After that, we go into the ACARS tab. Once we have selected some targets, we are not selecting real targets, but anyway, here we can see the information, ACARS information being gathered by public databases and also by our software-defined radio. On the middle, you can see messages. I have changed the names to keep a little bit of safety. And the mouse, the pointer, is now facing those two airplanes, are airplanes that are being monitored by this application. The longer they are monitored, the best information we have of them. And while I gather information, I tend to classify them in blue, so I don't have exploit for them, or red should be potentially vulnerable to my exploits. Okay? If we double-click on one of them, the red ones, we can see also detailed information of this airplane, specific airplane on a map, as we saw earlier. This is just an example. This is the exploitation tab, the final tab. Here we can see on the left, we have created three different virtual airplanes called Entrance 1, 2, and 3 with different flight management code. Okay, and on the right we can see different tabs also with some data and tools to work with. For example, this one is to the one that we are seeing now. It's for handling the FMS. We can start, stop FMS code. We can, as we see now, edit with an hexadecimal editor some of the data that the FMS is loading. I also have kind of a cheat sheet of the systems involved on this research, some of them just to don't get lost. As you can see, it's quite complex. And just in case I don't have the X-plane and the other laptop, just for a quick test, I can also run the flight gear simulator on the same laptop with 777, for example, to feed data to any of the virtual airplanes. Also, we have some detailed information. Whoops. Yeah. Before that, we also had all the APIs of the binary so that we can try to interact with them and see what options do we have. This is a kind of a primary plane display. You can see a drunk pilot flying over Berlin right now. Please keep in mind that this erratic flight that he is doing right now, it's just to monitor on real time visually what's the plane doing. Speed, attitude, altitude, and things like that. It's just to monitor, okay? And actually he's flying drunk all around Berlin. This ACARS tab allows us to, we have a lot of ACARS messages just classified, so we can select one, and below we will have kind of a template of an ACARS message related to route clearance or whatever, so we can modify and try to send and see what happens, okay? Finally, all of this is just to find vulnerabilities on airplanes. So if I press play, I get real FMS code running, and we will see right now how to manually load a proof of concept of a crash of a real FMS system. So we just tell the FMS to load some data I have prepared for them, and you can see that the FMS automatically crashed, and we have the 41, 41, 41, classic 41 of a crash. After that, we have to look if this vulnerability is exploitable or not. Okay, this is the end of the first demo. By the end of this demo, we have the virtual environment, the running code of the FMS, and vulnerabilities. So now it's time for part 2, plenty of time yet, where we will see how to deliver these exploits into the airplane with all the limitations we have, as we are not talking about common IP protocols, but aviation protocols. Okay. As I told before, there are the so-called ground service providers, two main players all around the world, which are SITA and ARINC. The first one is mainly focused on European field. The second one mainly focused on the North America and America. But now, for the last years, they are fighting in their eager to conquer the world, and so they are operating almost all of them in all the countries. As you can see here, they offer services related to almost every aspect of aviation. You name it. You have seen SITA for sure when you have to show your boarding pass before boarding the plane. You will see a SITA logo on the machine that's reading your boarding pass. And if you take a closer look, for example, when you leave Amsterdam, at the airport, you will see SITA mainly and maybe ARINC logos all around. Okay? Those are the two players. And they, among other things, offer to airlines, general aviation, to anybody that want to pay that, a service to be able to deliver and receive ACARS communication of all the airplanes of their fleet. How? Okay, these people are fighting, as I said, for the world domination on aviation services, so they have to offer the best services. Among other things, they offer all these easy methods in order to send and receive and manage all your fleet by using ACARS. From email clients to desktop applications, web applications, mobility, and if you don't have enough, you can even develop your own SDK, which is good because if you try to use their applications, you're going to find the same problem. You can only send standard ACARS messages. If you want to send something not standard, let's say to trigger vulnerability, you will have to develop your own interface. For example, the SDK comes in handy for that. This is extracted, again, from the same document of SITA. Okay, also we have the software-defined radio. We can use that in order to gain more detailed information on the local area we are sitting, because public databases usually don't cover all the ground. So for the local area, you can use software-defined radio with the appropriate hardware and software to monitor, deliver communications using a DSB or ACARS. Okay. Most of you already know what software-defined radio is. It's a system where instead of having to buy a lot of different hardware devices for each of the communications you want to work with, you just have to buy one or two devices, and by programming, you can implement all the specific needs for this communication. For example, the one I use on the picture is USRP1, Universal Software Radio Peripheral. And for programming, I use GNU Radio, LabVIEW, MATLAB, all these. Personally, I prefer to code in Python, but There are many. Here you can see a picture of an open source available implementation, draft, alpha, beta, as you want to call it, of an ACARS decoder. So software-defined radio, it's already working for ADSB reception, partially for ACARS. If you want to have sending abilities, take into account it's completely illegal, but you will have also to develop by your own. Okay. So we have vulnerabilities, we have the exploits, we have many ways to reach the airplane, and we can deliver exploits. So common post-exploitation is once you've reached the target, you have to consolidate on the target, establish two-way communication to interact with the target, and try to expand to other systems. Okay, and after that, go back to discovery and start again. For example, as you can see there, the new Boeing 787 has plans to switch to VxWorks, and it will host up to 8 to 100 applications, including the Honeywell's FMS, good luck for us, and health management software, oh, sounds creepy, crew alerting and displaying management software. I don't know if you ever exploited a real-time operating system, but once you are inside, okay, I will end up there, okay? So, the FMS as a post-exploitation, that's a diagram of official documentation on flight management system and general avionics. It's connected with few other systems of the airplane, more approximately all of them, okay? So once you have the flight management system, you can try to target some of those systems also in some way. For example, engine and fuel systems, maybe or not, they can have a computer. You can think, okay, flight controls is just wires. You pull the control column and a wire is moving the aileron. Wrong. On modern airplanes, you have the so-called fly-by-wire, which is just a side stick, some wires going to 3 different computers that do some calculations, and after that, the computers move the aileron. Can be exploited or not, this is not within the scope of this talk, but as you can see, the FMS looks like the perfect place to start up to conquer all the systems of an airplane, okay? So aircraft post-exploitation, it's kind of tricky. As you can see, a picture of the autopilot engage-disengage control. This is kind of our enemy, because if we want to somehow control the airplane, we have to try to convince the pilots to don't disengage the autopilot. Good news are that aircraft and pilots are quite predictable because they follow checklists. We follow checklists and procedures for all the normal operation and also for all the emergency operation. On the emergency procedures exam of an airplane certification, you have to have 100% of success on the exam. I mean, you cannot miss a single step. So by having the checklist and procedures of an airplane, you can somehow know what's going to do the pilot under some circumstances, okay? And we have to avoid what you can see there on the left, on the top, autopilot disengage. We have to try to avoid that, okay? After that, we have to try to exploit other communication and navigation systems or protocols. As I said, ACARS, ADSB have some limitations. If we go over these communications, we can control them, we can overcome these limitations, and also we will be able to send some messages that would be discarded by the systems if we don't take care of that, okay? As I said, planning and timing is everything. If we do proper timing and proper planning, we can convince the pilot that it's happening something, knowing how they are going to react, so we can not just avoid them to disengage the pilot, but also we can even trigger or make them to help us into doing what we want, kind of return-oriented programming, but for pilots, okay? I point you to this address, so I know you are going to do this. It's kind of pilot programming. And after that, establish a command and control, as always, establish a two-way communication, so we can send further actions to the exploited airplane and try to overcome the limitations as the ACARS and ADSB ones. Okay. Simon. Simon is the name of the post-exploitation agent I have developed. Why to develop such an agent? I mean, The idea was not just to find vulnerabilities on board the systems, see if they are secure or not, and try to fix them, working with the manufacturers, but also see how dangerous could be to take over one of those systems. For that, I had to develop Simon. Good news is Simon cannot be used on real airplanes because I developed that for the x86 platform, just for my virtual environment, so we are kind of safe. And Simon is a multi-stage payload, first stage to upload the second ones, try to control a little bit the ADS-VA cards in order to upload the second stage and the third stage. After that, we gather a little bit of persistence, because once on ground, usually you turn off all the systems at some point, and we would like to keep the control of the airplane, even if they shut down the FMS for a few hours. Stealthness, we don't need to go into a rootkit, because as you can imagine and see over there on this cockpit, there is no way you can just try to list all the processes being run on the FMS. So as long as we don't show anything strange on the electronic flight displays, all those screens you can see here on the 380 cockpit, pilots won't care about. So we don't need to go into the rootkit just to try to be a little bit silent. So what can Simon do once uploaded and established and running on an FMS on board an airplane? We can upload, change, modify, or remove flight plans or databases. The FMS has many databases for radio aids, aircraft performance, custom airline data. We can try to modify some of them, or just completely delete, remove, or upload a new one. We can upload payloads, kind of scripts. We'll see later that. Plugins, which are just additional code that can improve the abilities of Simon, or just send specific commands to the airplane, and also it takes care of the two-way communication. Okay. So that's a demo time for the exploitation phase. Usually that was just this black screen we saw before, all this command prompt with Simon, the name of the plane. But for many reasons, like to further highlight the importance of these security issues, also in order to improve the visibility of all that, many months ago I decided to switch the platform. So instead of having one base station running all the virtual airplanes, software-defined radio and everything, and another laptop launching the attacks, I decided to move to something more comfortable to wear and take with you, like, for example, a mobile phone. Okay, now I feel a little bit like Steve Jobs showing a new device. So I'm going to show you a beta version of an application I developed for Android that we can use in order to hijack airplanes. Ouch, I broke something. Okay. Yeah. Here it is. Here you can see a normal Android device with a stock ROM, no routing, no special features. Even it has not the standard Android ROM. It has the Samsung one, as you can see. Okay, and this one is the one running the application. Okay, so the first thing we have to do in order to hack, hijack, or attack airplanes with a mobile device should be to go to settings, go to more settings, and of course turn the device into airplane mode. It looks like obvious. Anyway, just kidding, because I need the wireless, so I didn't switch it to airplane mode. Okay. No, really. One thing our application is offering us is notifications from time to time of the potentially vulnerable airplanes that are nearby our base station. The base station is always collecting information on the airplanes nearby. It gathers ICAS information, and when some of them reach kind of a threshold, like 80-85% of exploitability, they send you a push notification, and you can see here, I removed the names. You can see just the virtual ones, but you can see the available potential targets, just to keep informing you on real time. Also a widget, just to see at any moment which ones are, okay? After that, we can just start the application, which is called Plane Exploit. I know the name is not that good, but I didn't have that much time to think about it. The interface, the ugly interface, it's also divided into the same phases. We have discovery, information gathering, exploit, and post-exploitation. For discovery, for example, which is to just plot and see which targets we have available. Oops, what the hell I did? There. I think I broke something. If you don't mind, I will start again. Okay. I'm going to move a little bit. Yeah. Whoop. Yeah. Here. Yeah, almost. So, here we are. The first thing we can do is to just start up an external application offered free to us, available in the Play Store, which is called Flight Radar 24. Most of you already know about that. That shows up all the airplanes. We can have detailed information on the airplanes, but also if we have kind of a local target we want to get information about, we can always switch to augmented reality view. This is and you can see here all the available targets using just your camera and moving around with augmented reality, okay, just to face the local ones. After that, we can just select the target, and in order to be able to keep working, we can just go to share and share the available target with our application. As you can see, as you can see here, the target has been selected. In this case, this one, just a random one. Okay, I don't know if it's even vulnerable or not. We can also just go into this huge list of nearby aircrafts that is being updated from time to time, or we can just select the virtual airplanes, which is what we are going to do today. Okay. After that, we go into the information gathering. This has just one purpose: give us the information we have, and one additional button that will tell, please communicate with the base station and tell me if this target looks like vulnerable or not, based on the information we have been gathering using ACARS. This kind of passive OS fingerprinting. We wait a little bit and we say, okay, the target is exploitable, fine. Then we can move into the exploit. The exploit is just a big button where you press and you deliver the exploit and upload Simon. The video is quite fast, but anyway, this is a virtual environment. In real world, should be quite slower. Okay. Now we are supposed to have we have on a virtual environment a target airplane with the FMS exploited and Simon updated. So we have the post-exploitation phase now. One of them, do you remember the drunk pilot that we saw before? Okay. Now we can see this same pilot being flying smooth. What's happening here is I'm using this application, open source. I connected that to the Android API using the phone app. So with the accelerometers, we are controlling the plane a little bit up, down, right, again, left, and up. Okay. Also, if you don't want to be flying manually your airplane, which I understand can be annoying and time-consuming, you can just say, okay, please go here, and you can see that the plane directly faces there. It's always faster, okay? Also, you remember that we could upload scripts. Okay, this is the script editor, which I call the payload editor. Payloads for Simon are divided in two components. First of all, it's a trigger point, and after that, the action. Trigger point defines where is this action going to be executed. So we have to select some coordinates. Easy, we go to Google Maps, select some place. We share this place with our application, and you can see here that the trigger coordinates has been established. So we have a point at which the airplane is going to do whatever we tell them. Well, maybe not the airplane, but Simon. Problem, it's really hard to make an airplane to fly exactly over those coordinates, so we can define an area. An area by the radius and also bottom and top boundaries. So whenever this airplane flies within 10 kilometers, between 10,000 and 35,000 feet, the action is going to be executed. Which actions? Okay, I have some of them, like make more friends, which means look for another planes and try to go over them, okay, air-to-air, hijack. Visit ground, I don't have to explain that one. Kiss off, usually means we have been discovered, please self-destroy, don't leave any clue behind. Apply new flight plan, so we can upload a new flight plan and it will get executed under these circumstances. Chat a little, just opens a two-way communication with the screens and printer of the pilot, so if at some point you want to chat with pilots, apply this action and you can just start talking with them. do introspection. That means try to go into other systems on board the airplane. Which means just to stay quiet, they are looking for us, and be punkish, the last one, on the films, that sometimes all the masks drop, the lights start to blink, people screaming, and the airplane, that's your payload, okay? We just will select something like shh and apply, okay? The action is selected, we update the payload, and the payload is successfully uploaded. Now Simon has another trigger point, and whenever the airplane flies within this area, this action will try to be executed. Okay. Also, I will show you some other things I'm developing. If we turn the phone, which you cannot see here, you can see a map of the targets to have always in view. And also you can see another list, which is toolbox. I have two different tools that come in handy when you have to program Simon, for example. Okay, those tools that are not working within plain exploit, but there are similar tools also available for Android are, for example, Boeing 737 checklist. As I told you, it's really important to know what's going to do the pilots if you trigger some action. So just to quick check what's going to happen and plan better your actions, you can have on your phone the checklist of the target airplane. And another one is a professional application used by pilots in order to planify flight plans. Flight plans are not that easy. You cannot just point to a point and the plane will go over there. You have to take into account radio age, altitudes, airplanes, airfields, airspaces, a lot of things. So it's always good to have a tool like this one to properly planify flight plan. As you're going to hijack an airplane, at least do it properly. So do a proper flight planning, okay? And with this tool, you can always just select the radio age and the flight area and do a proper flight planning, okay? At the end of the demo. Okay. So, thank you. I know it's been a lot of time, but just 2 more slides, okay, conclusions, 1 more slide. Remediation, okay. Usually on aviation, people tend to speak a lot about security, but they mean safety. So you have 3 times the same system just in case 1 fails, or 2 fails, you have still a 3rd one, so you can keep flying. But they are not meaning security as we all know security. Their systems are not ready to face this kind of attacks. Okay? So in order to fix that, first of all, the next-gen security should be improved. Next-gen is next-generation airspace being deployed and even designed right now. Among other things, it includes ADS-B technology and ACARS. So if they are still deploying them, maybe we are on time to try to fix them and give them a little bit of security. Just a little bit, please. Also, more systems should be reviewed, looking not for safety issues, but for security issues, like the normal vulnerabilities we are always facing in our everyday work. Okay, who should take care of that? Manufacturers, because they are making these systems ground service providers. I think it's important because they are sitting in the middle of us and the airplanes, so they should take care of the security of their systems, installations, and also airlines. I mean, airlines, they don't develop these systems, but they are the primary affected because they are using these airplanes in everyday basis for their business, so they should take care of. Actually, we are working with my company, Embrace, with EASA, European Aviation Security Agency, to improve this situation. We'll see if the S of security really means security or safety. We'll see. I will tell you, okay? So, some references for you. I know I've gone over some of these things quick, but I didn't have time. I already talked too much. So you have here some references for you to read if you want to go deeper into this. And I would like to thank all these people that has helped me somehow. Final word before the questions. You know that behind a good research, there is always a great woman. So in my situation, thanks to Shelley for everything. And that's all.
Questions? 1. In a real-world situation, would you have to be on the plane with your Android phone to take over the control, or can you do it from the ground?
I'm sorry?
In a real-world situation, would you need to be in the plane as a passenger to take over the plane, or can you do it from the ground?
I have one rule. Never hack the airplane you are flying on. I mean, can be like, oh shit, it was Little Endian and you are crashing. No. No, I can do depending. If you are, you can always be on the ground, of course. If you are using software different radio, you are just limited by the scope or the range of your antenna. And if you are trying to use any of those ground service providers, which is illegal, but if you manage to do, then you have almost worldwide coverage. But you can always do it from the ground. It's not a good idea to hack an airplane while you are over there. No, don't try.
Any other questions?
What's been the reaction of the industry about these ideas and these exploits? Are they scared? Are they saying, ah, it's not going to happen? What's the attitude?
Well, we'll see. We've been in contact with them for just a few weeks, months yet, since we announced this talk. But at the moment, I must say that I'm surprised because they are facing the subject. They didn't deny it from the beginning. They had listened to us, they considered everything, and they put us in contact with all the... They are trying to help us to check all this research on a real, complete hardware airplane. So they are not denying everything, they are not hiding, they are not saying... They are just trying to collaborate with us to try to see if everything is really working or not. They think that should be, so they are offering resources and they're willing to solve the problems. So yeah, I'm surprised, gratefully surprised.
Yeah, sounds good.
Yeah.
Do you know if any other groups are working on this, playing this?
I always thought that I was not the first person to do a research like this one. Maybe I'm the first one trying to get that, to do that public and to work with these authorities to fix the problems. But I didn't heard about any other person doing that, but I'm pretty sure I'm not the first one. Cannot be.
Thanks. Great talk.
Thank you.
Is it likely that it's possible that it's going to be updated on current planes, or is this something that's going to linger for many, many years until the planes go out of service because they don't get firmware updates?
Sorry, no, I think I understood two words. I'm sorry.
Okay, sorry. Is this something that is likely to be fixed on current planes because they get firmware updates, or doesn't that just happen because it's really sort of a long and cumbersome process?
Yeah, that's a question mainly for the manufacturers, but for my knowledge of the systems, we have two different groups. We have what the so-called legacy systems, the older ones from the 70s. I think it's going to be really hard to fix them in a proper way, but yeah, an initial improvement can be done. But take into account that it's older code, a lot of things should be changed, and it's really spread all around the world, so it's expensive and hard to fix, mainly because the software has been tested for years, everybody knows it's safe, it works perfectly. Any modification you add to them, you reduce that safety. On modern systems, yeah, you can, it's easy because they have been developed better, they have even a little bit of security in mind, so it should be easier to be fixed. But that's my opinion. You have to talk with manufacturers, which are the ones that really know their systems.
Thank you very much.
Thank you.
Anyone else?
Yes, I'm not a commercial pilot, or a pilot of any description. I'm just wondering if you were flying the aircraft, what options do you have? Can you reboot everything and switch off ACARs so you don't get hacked again, or are you finished?
Yeah, a good question, of course. The question should be, is possible to switch off ACARs? Let's say it's possible, yeah, that would be a solution for the ACARs vector. Remember the mind map? Okay, ACARs is just the one we are using today. If you remember that, it was plenty of other branches. But yeah, in order to face the ACARS approach and to try to avoid that, should work if it's possible. Imagine that you discover that your FMS has been actually compromised. Depending on the airplane model, by switching off the the autopilot, the activities that the attacker could do would be decreased. Okay. The ideal situation would be to completely turn off the autopilot, de-FIS everything, and just try to fly the old ways, as the older days, just with the few analog. I'm trying to go back 1 minute. This is, for example, the 380 cockpit. Okay, please point me to one older analog system you can rely on, like a compass, an attitude indicator, an HSI, something. You can see maybe here one. Come on, you see that? This is a keyboard and a trackpad, a touchpad. Okay. This is not a control column. This is a heads-up display, and you don't even see the control column. It's over here, and it's a side stick using fly-by-wire, another computer. So there is little you can trust. But yeah, of course, by turning off almost everything automatic, flying like the old days, you can just reach a safe airport and land again, no issue. In order for this to happen, the pilot should realize that something is going wrong and think, okay, what can be happening? I'm running out of fuel. No, I think I have plenty of feed. I'm having a stroke. No. Oh, yeah, somebody hacked my airplane. It's hard for pilot to go into this. But if they manage to do that, or they know, or whatever, yeah, there are some things they can do. It's not that dangerous, at least on some planes. Depending on the airplane, the model, there are more advanced ones, less advanced ones. You have an old Tupolev, there is no way you can hack into that. I mean, everything is going on wheels and no problem. But into a modern like the 787, 777, 380, all this new stuff, and also the older one, they are always updating, adding new systems, which is even worse because they have to make new systems work together with old system and some other new systems. So you can imagine this is kind of a mess. And security is not something that they take into account when they have to integrate all these systems. It's not a direct answer, but more or less you can, approximately you can know more or less how it works.
Hi.
You were first, but don't worry.
Yeah. I mean, if you were to target an airplane, would you have to do some first do some research to find out what kind of systems does it have, or can you target a range of planes or a range of models, or it's different from company to airline to airline, the flight systems that they have on board?
If I understood properly the question, that's the reason I have, or the reason for the existence of this base station, collecting always information on all the available airplanes. The more information you have, the better, because, for example, a 737, depending on the model, on the airline, on a lot of things, can have completely different systems. And you have to try to be certain that at least the ones you are going to target are the ones you think. Because, I mean, if you do a mistake, maybe you are going to increase the counter of death, and you don't really want to do that. So, yeah, the best information, I think I can get up to 85 to 90% of certainty about a specific target, but I never tried, of course. I have a database I collected of public information on different airplane models, airlines, and everything. So I'm always comparing the information I have about an airplane with the information of this database. And whenever I reach a certain threshold, I put it on red or in blue.
Yeah, but the vulnerabilities are different for different flight systems.
Yeah,
right?
of course.
One more question?
Yes, so you told us you got some like cheap flight management systems off of eBay. Did you actually try to port your exploits to those real world systems, or did you not do that?
Yeah, to be honest, when I faced this research, I always had in mind why I did that for. And I did that because I wanted to know how secure those systems were, the scope of the vulnerability and everything, not to target real airplanes. So under the same circumstances, I always have chosen to get the code, which is the real code, but on a PC platform, so I can do exactly the same my research, but my exploits, Simon and everything will be harmless into the real world, so to keep things safe. So I know that vulnerabilities on the same code exist at the same time on both platforms, but the exploit won't work, which is good, because I don't need the exploit to work on the real hardware to know that the vulnerability is and if it's exploitable.
So let's give the assumption it's really the same software.
Yeah.
Okay.
We can do one last question. Doug, 2 more questions? Okay. It's the last talk of the day, so we're gonna spill over and have added time because of the interest. Okay. I think he comes first, and then after that, is that all right? Oh, were you first?
I don't mind.
Right. And then you come right.
Okay, how scared should we be, actually? I'm here.
Who's talking?
Here.
Oh.
In front of you.
Yeah,
Yes.
thank you. I saw him with a microphone. I was expecting him to talk, and it was shocking.
Sorry. So the question is, how scared should we be? Is it possible for countries to take over UAVs or something like that? Is it the same system?
Okay, again, please, sorry.
Is it possible for other countries to take over UAVs or something like that?
Oh, UAVs.
UAVs.
Yeah, drones.
Yeah, drones.
Yeah, although in Spanish, as I said, my research is about aviation, so if it flies, it should be within my research. Cannot give details on drones, but you have a talk in Spanish, that's a problem, about the preliminary results of one of the attack vectors over drones I did 1 year ago. You have it on my website. Should be, this is in German, so I will do it the easy way, which is all the way back. Okay, here you can see the commandercat.com. There at some point, somewhere you have the link to this talk. It's in Spanish, but at least you can see the slides about initial research I did on that. The only idea of the research was not to mess up with GPS, because it was already well known, not to try to attack the command and control link that the normal operator uses, because this is pointless, but to try to figure out another attack vectors. You have some information there, but I cannot talk about ongoing research on this field. As I said, I focus on aviation. If it flies or has something to do with aviation, should be on the mind map. Yeah, thank you.
Okay, so the trend in the security industry is that the exploit to patch time is shrinking, right? I mean, it used to be, quite a long period. It's now getting down to a couple of weeks, hours if necessary. The quite correct safety-first culture in the aviation industry, of course, is to take as long as you absolutely need to convince yourself whatever you're doing is safe. So the Dreamliner incident going on at the moment has been running for a very long time and is costing Boeing an absolute fortune. In your dealings with the authorities, are they stepping up to the plate in terms of realizing that, they either have to ground everything, which they're not really prepared to do, I imagine, or they're going to have to really get to grips with, changing their internal processes and procedures to be able to do things in internet time, which they've really not been used to doing?
So if I understood properly, in short, the question is, how are those authorities, manufacturers, and people going to face the solution of this problem? To be honest, I think it's on one hand too early to say that, because we've just been in contact for a few weeks, months yet, nothing is ongoing yet. But also, as I said, I feel comfortable with their initial reaction. I don't know what's going to happen. Maybe you have to ask them. It's a huge problem. It's not easy to fix, because you can fix, as you said, one vulnerability, 2 vulnerabilities, but the problem here is that the technology by itself, at least the one I have checked, is not secure at all. So it's not easy for them. I don't know how they plan to do that. I will keep you informed if I can. I don't know.
All right. Thank you. I believe that wraps up the Q&A session, and also it means it wraps up all the talks for today. Thank you very much, Hugo.